Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 3. Student, basically this lecture was the design of reinforced beam, doubly reinforced beam, as we recorded lecture number 1 and lecture number 2, but I have already recorded lecture number 3, but in that lecture there is a little bit sound problem, so that's why I'm recording this lecture again. In lecture number 1, basically we covered the some kind of theoretical portion of the W reinforced beam, while in lecture number 2 we covered some examples, right? And in this lecture, this is lecture number 3, we will cover this example 5.9. Okay, so before we start this lecture, I have to recall some important points that you people must be remember while we are designing a doubly reinforced beam. As you people understand that in a doubly reinforced beam we have to provide a tension reinforcement as well as a compression reinforcement, right? This reinforcement is represented by as prime, while this reinforcement is represented by as, but this is further equal to as1 plus as2, right? And sometime this as prime equals to as2, but this condition will be satisfied when, remember, when our fs prime equals to fy, right? When fs prime not equals to fy, remember, then in that case as prime will not be equals to as2, and in that case as2 will be calculated by using the relationship as prime equals to into fs prime equals to a s into fy, right? This is the relationship from which we will calculate the a is 2, right? This is not as prime, this is a is 2. So a is 2 here equals to a is fy divided by a fs prime, right? So this is very important relationship. This relationship will be used when this condition is not satisfied, right? So this is very important, and you people must remember this condition. This is important, right? So I already write down this right here. You see, when fs prime equals to fy, then s prime equals to as2, but when fs prime not equal to fy, then you have to use this relationship, and from this relationship your as2 will be this one, and as1 will be recalculated. This is as minus as2. As is the total tensile reinforcement, this one, right? And as is further equal to as1 plus as2. The difference between as2 and as prime is this, that as prime is the theoretical compression reinforcement, which we basically calculate from the formulas. As2, this is the actual compression reinforcement, which we basically provide to the system, to the section, right? This is very important to understand. I will clarify this thing in later stages, but at this time you must remember this, right? Next is the example, which is example number 5.9. So this example is basically the design of a doubly reinforced beam, right? Now the section is already given, right? And this example is basically from the MC Cormic book, right? MC Cormic. So here we have this section, which is right here. You can see the section is 15 inches wide, while 31 inches total depth, 3 inches is the top uh, effective cover, while the 3 inches is the bottom effective cover, right? And the live load movement is given, right? The dead load movement is given, right? And FC prime is given, right? So Fy is 60,000 psi, right? So what we have to do, we have to find out the ultimate moment, which is mu. Okay, so this is simple. Mu is equal to 1.2 md plus m 1.6. You just plug the value. Md is given, ml is given, you will got 1030 feet kip, right? Now uh, when we are designing the doubly reinforced beam, we have to use the assumption, as already we discussed in lecture number 2. We have to assume that, let's say, fs prime equals to fy. This is the assumption, and we have to use this assumption that fs prime equals to fy, right? Now so using this relationship, we will check in later stages this assumption. So checking whether rectangular or double reinforced beam, yes, this is also important. This is the first stage, right? This is the first stage, sorry. This is the, in second stage we will use this assumption, but this is the first stage, that first of all you have to use where we need to use doubly reinforced beam analysis or single reinforced beam analysis. This is very important. Sorry for this mistake, sorry. Checking whether the rectangular or doubly reinforced beam analysis is needed. So find out the row maximum value. We already know the value of row maximum, that is 0.85 fc prime beta 1 into fc prime divided by fy 0.003 divided by 0.003 plus 0.005, right? This is the value which is used for row max, although this is the same equation for balance steel ratio, right? So you just need to plug all the values. All the values are given. We will got this value, right? And we will find out as max, right, which is equals to as1. This is very, very important, right? As max equals to as1. As max is therefore, because we are using row max, so that why we are using that why max, because we are using the maximum steel ratio, right? Why we are using the maximum steel ratio? This is very important because as we know that in singly reinforced beam, when we are going to design any singly reinforced beam, we always use that our row provided should be greater than our row minimum, while it should be less than row max. This is the check, right? This is the check. This is the ductility check, or you have to ensure the yielding criteria, right? So here we are assume that, let's say we are designing this reinforced beam as a singly reinforced beam, and we are giving the the maximum steel ratio, means that we are equating our provided steel ratio with the row max, right? So uh, this is the reason that we are using the row max value, not the row minimum value, because we will increase the row provided from row minimum to row max. After the row max, we cannot increase, because ACI code do not allow us to increase the row provided from the row max, because if we bypass this condition, this will leading us toward the over reinforced beam, right? So that why when such condition exist, such condition prevail, in that case we have to design this section as doubly reinforced beam, right? This is also one of the reason. So here you can see that we calculate AS1. AS1 comes out to be 7.60, and we calculate the A value. How to calculate the A value? We already know that A is equal to AS1 Fy into 0.85 Fc prime into B. So Fy is given, B is given, that is 15, Fc prime is given. So by using this relationship, we will find out the A value, that is 8.941. After that, using the basic equation for the ultimate moment, remember at this stage this is 1, right? It is denoted by 1. So this is the one of the basic equation you must know. Mu is equal to 0.9 Fy into D minus A divided by 2 into AS1, right? So by using this equation, we just plug all the values, and what we got at 04.4 feet kip, right? Remember this is in KSI, so that why this is the value is in kip, right? Now Here you can see that the value is our ultimate movement capacity is 1030, and here we have at 04.4 feet cap. So the design capacity or the section capacity is less than the ultimate movement capacity. So that why, as you see here, we needed a doubly reinforced beam analysis, right? We needed a doubly reinforced beam analysis. So now we need to convert this capacity to the nominal capacity. So how to convert this into nominal capacity? You just need to divide this by the value of P, that is 0.9. So dividing this by 0.9, you got 893.8 feet cap. And similarly, you have to convert this ultimate movement capacity to the nominal movement capacity by just dividing it by 0.9. So we got 1144.4 feet cap. So this is now our Mn value. This is our Mn1 value. Now from this, we will got Mn2 value. Mn2 is what? Mn minus Mn1. So by using this equation, you see the required value for which we have to design the S prime value, which we have to find out the S2 or S prime value. This is 250.6. We have to increase the steel ratio and we have to insert that ratio, that steel here to support this extra moment, right? So now, so checking to see whether the compression steel is yielding or not. Now, so as we got the A value, that is 8.941, right? So this value is clear. Now remember, the A value is already we calculated it, right? So here we have to calculate the Fs prime value because we have to check this assumption, right? We have to check this assumption that whether our Fs prime value is equal to R, whether it is greater than Fy value, right? So remember, this is the compulsory criteria that you have to check these two values, whether it is greater than Fy, whether it is equals to Fy, whether it is less than Fy. If this value is greater than Fy, this means that our compression steel is yielding. So if it is yielding, so this means that As prime equals to As2, right? So here we calculate the C value, which is C divided by beta 1. So this one, right? Fs prime, the equation is already given 87 sometime or 87,000 divided by 1000 to convert it into kips. This is C value, right? You must remember this. This is important equation. 87 sometime 87,000. Same. C minus D prime divided by C. Okay. So here we have, this is D prime, which is already given, right? This cover is D prime, right, which is 3 inches, and from the bottom it is also it is CC, right, which is also given, that is 3 inches, right? So 3 inches is given, that's why minus 3 divided by 62 KSI. Now this means that our assumption is okay, mean that the compression steel is yielding. If this Fs prime is less than Fy, that is 60,000, so this means the compression steel is not yielding, right? So as Fs prime is greater than Fy, so the compression steel is yielded and Fy equals to Fs prime. So when this criteria is satisfied, means that this condition is prevailed, right? So uh, now what we have to do, we need to calculate the theoretical compression reinforcement, that is S prime Mn2. Remember, this is very important. We have to use Mn2 value, not Mn1 value. Fyd minus D prime. Remember, so already we know the value of Mn2. We already calculated it and 12 to convert it into inches because the movement is in kef feet. So multiply it by 12 to convert feet into inches. Fy is given, and D, that is the total depth. Remember, we have a section right in this form. So here we have right there, we have 3 inches, we have 3 inches, and this depth is given, right? This depth is how much? That is 25 inches. So 25 plus 3 are 31 minus 3. It will give you the value of D. D value is from the center of this steel to the top, which is our D value, right? So what we have now, we calculate the S prime value, which is 2 square inches. Now 2 square inches, we will use 2 number 9 bar, which is exactly give us 2 square inches, right? Now as we know that Fs prime equals to Fy. Remember, this is very important. Somebody may ask that this is 62 and Fy is 60, so how we can say this is this is same? But remember, we should not consider the Fy value more than 60. We always take it equals to Fy, right? So from this condition, I already in the beginning of this lecture that if this condition prevail, this means S2 equals to S prime. And now S, I already mentioned this, S1 plus S2, this is the total reinforcement 9.60. For this reinforcement, we will use 8 number 10 bar. So 8 number 10 bar gives us 10.12 square inches. Remember, this is very important. The difference between this one and this one, we are a little bit increasing the actual value. That is, this is the reinforcement which we are giving to the section, but this is the theoretical reinforcement which we basically needed. So there is a little bit increase, right? Remember this increase. This is I will share this, right? It's important. Now, important note. Here we are checking the epsilon t value, right? It should be noted here that if the bar size are so selected that it gives you the exact amount of steel as calculated from formula, then the value of epsilon t not changing and it remains 0.005, right? But the selection of bars in such a way that quotes, this means that as in this case we see that we are using 2 number 9 bar, which exactly give us the same reinforcement which we basically theoretically needed. But here if you look that theoretically we need 9.60 square inches area, but practically we are providing 10.12 square inches. So this increase, a little bit increase, if you just subtract 10.12 minus 9.60, it will give you 0.52 square inches. So this is increase. If you are increasing this value means if you are increasing the practical or the actual steel reinforcement from the theoretical one, so it will affect the value of p value. Okay, as we are using 0.9, but this 0.9 will be accurate when you are not increasing this value from the theoretical value, this one. If you are increasing, this will affect this value, and this value will further, because remember, basically if you are going to increase this value, it affect epsilon t value, and that epsilon t value will affect this one. I will share this one, okay, right? Next, not possible. Remember, in practical, in actual, there is not such bar, you can't make such bar arrangement that you should provide the exact amount of reinforcement which will exactly give you this amount of reinforcement. We have to select such bars which is close to this value, remember, in actual reality, right? So let's see. Now here I already discussed this point, right? So therefore checking epsilon s prime, epsilon t and phi value. Once if you do such kind of uh, bar arrangement or bar selection, so then you have to check your epsilon s prime value, epsilon t value, and your fs prime value. Okay, if you make such kind of um, arrangement of reinforcement which is more than the theoretical reinforcement, if the actual reinforcement and theoretical reinforcement are same, so you don't need to check this value. But if you increase the value, then you have to check these values. So let's see, we are checking we recalculate the value of a. Now at this time, remember the value of a will be what? Will be a is 1, right? A is 1. Now a is 1 is what? A is minus a is 2, right? Into fy divided by 0.85 fc prime into b into beta 1, I think so, into b, sorry, into b. So this is, remember, a is now, this is not the actual value 9 points, because here a is 10.12, so that why we are using a is minus a is 2, right? So a is minus a is 2 into fy divided by 0.85. We just, you see, 10.12 minus 260. So that why the a value is now 9.55. This is important because in the first stage we see the a value is what? The a value is 8.94. This is 8.94. And now the recalculated value is 9.55. This means that the the thickness is now increased. The thickness of the concrete block is now increased to this one, because in the first stage the thickness of the concrete block is this one, 8.55, right? It is close to the top fiber. That's why ductility is ensured. But here you can see the increase in the depth of the concrete block. It means it leading towards the over reinforced beam behavior. Here is the under reinforced beam behavior is sure, but as you increase the A value, which leading the neutral axis towards the tension zone and increasing the compression zone area, so that why it leading towards the compression, the over reinforced beam behavior. So let's see whether our check is are okay or not. So recalculate the value of c. C is what? C means a divided by beta 1, right? So from this is given beta 1 is 0.85. We calculate this one. Fs prime value is again calculated, and again ductility is ensured. This means Fs prime is greater than Fy. This means that the yielding is ensured, right? And the yielding will be occurred. Now, epsilon t value. So as we know that for a ductile design, the epsilon t value must be greater than or equal to 0.005. If you want uh, to design the reinforce as a ductile, or the ductility check will be okay, so you must ensure that epsilon t value must be greater than 0.005. If epsilon t value is greater than or equal to 0.005, this means what? This means that your phi value is 0.9 is okay. If your epsilon t value is less than 0.005, so this means what? This means that p value is not equal to 0.90. So let's see, we calculate the epsilon t value, and the epsilon t value is 0.0044, which is less than 0.005. That means the ductility check is not okay. This means the phi value is 0.9 is wrong, right? We have to calculate um, the exact value of p value. So here I have mentioned you some important information, to share you some important information which is very very important that you people must understand. Remember, there is a relationship between the epsilon t value and the p value, right? Epsilon t value is let's say it starts from 0.0022 to 0.005, and here we have 0. The phi value should be 0.65 to 0.90, right? These two values must be remembered. There is a horizontal curve, right? And then it goes like in this shape, and then again it becomes horizontal. So here you see this value and this value. The epsilon t value, which is more than 0.005, this means here we will, and this is the tension zone, mean that here your beam will behave like an under reinforced beam. This is a tension control section, and at this stage your p value will be 0.90. If this epsilon t value is equals to 0.002 or less than, so this means that we are in compression zone. This is a compression zone, right? This is a compression zone, and in this stage your p value will be 0.65. But if the epsilon t value is greater than 0.002 but less than or equal to 0.005, less than, so this means that we are in this zone, and this is the transition zone, right? Transition, a very important discussion, remember. And here you have to interpolate the value of p between this value and this value. So here we will use the equation of ACI equation, which is 0.48 plus 83.3 into epsilon t. From this equation, we will calculate the exact value of p, right? So as we see that, remember these conditions are very important, right? When your epsilon t value is 0.002, this means your p value is 0.65. When epsilon t value is greater than or equal to 0.005, this means your phi value is 0 0.9. But when your epsilon t value is greater than 0.002 but less than 0.005, in this case we have to calculate the value of p, and the value of p is equal to 0.48 plus 83.3 into epsilon t. This is important. So as the calculated value now p is 0.0044, so it is less than the 0.005 but greater than 0.002. So we have to use this equation and we will find out the exact value of p. Now the exact value of p is what we will use the equation. We just plug the value of epsilon t, that is 0.0044. We got the p value 0.85. This means the value which we are used in the previous calculation, that is 0.9, right here, right here, this value is wrong. Okay, this value is wrong. Now the exact value is now p is equal to 0.85. So the reduction, this, what the effect of this value, that it will reduce your capacity of your movement. Okay, because from 90% to 85% we are 5% further reduction, so this will further decrease the movement capacity of your section. So let's see how it affect the ultimate or the movement capacity. We are again using the same equation, the movement equation. Now we are using 0.85, not 0.9, because we adjust this value. So the basic equation, which is what, right here you see here, this one is the basic equation, which is mn equals to uh, p value. Okay, because this is the as minus as1, right, and into fy into d minus a over 2, right, plus a s2 into d minus d prime into fy, right? This is the equation. So here we have as minus as2 into fy into d minus a over 2 plus this is the as2 into d minus d prime, this value d minus d prime is 25 and fy is 60. So the moment capacity is 12168 inch cap. This is important. 12 inch cap, right? Dividing it by 12, we got 1014 feet cap, which is less than 1030. This is important. Now you see the effect of the phi value. Okay, because we reduce the value of p, so it will further reduce the moment capacity of the section to 1040. Now Here, if you see, closed we are close to the desired moment capacity, although the design is okay and will work, all right, but theoretically this design is basically is not fulfilling the required criteria of the ACI, because as we see that MD should be greater than or equal to MU. So here, mm, although a little bit decrease in the value from the examination point of view, it is okay, right? You can write this that it will work because the result is closed. You can write this like in this form to mu, so it is okay, it will work, right? But if you somebody interesting to 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 increase this value or to equate these two values, so what we have to further do, what we need to do, we have different options, right? We have different options. Now what are those options? See, as we can see that the beam capacity is somewhat smaller than the mu, it is due to the variable factor p. If we choose the bar size in such a way that gives us the exact amount of steel and p value not to be changed, means p value is 0.9, then the value of pm is 1073 fit cap. If this value is not changed from 0.9 to 0.85, if it remains 0.9, then the moment capacity will not be that one, 1040 fit cap, but it will be 1073. If we choose the AS value exactly what we need, because we choose 10.12, I think so, which is a little bit larger than the theoretical one. So that is the effect which affect the value of P, and P will affect the capacity of the section. Now, if you want to correct or if you want to increase the capacity, we have three options. Either we need to change the dimension of the section, which is not possible in this case because we are bound that the dimension should not be changed. Increase the value of Fy and Fs prime. This is possible. Although Fy cannot be increased to, it can be increased, but in our actual in our area we have only available steel is 60 and 40 KSI. So that by Fy is already bound. We are bound, although there are different 80 grade 80 steel is also available, but in here in Pakistan I don't think that people will use um, Fy 80 KSI. Although in our local uh, construction Fy is 40 or 60 KSI, right? Fs prime is possible that you will increase the value of Fs prime. Now here is the third option. The third option is very unique option. The third option basically explain that as we are if we look to the value of a is that is 10.12 and theoretical value is 9.60, so a little bit increase, which is a is minus a is 1 is sorry, the the difference between 10.12 minus 9.60 is 0.52 square inches. This is a little bit increase. So here the third option is basically explain that as there is less difference between the demand and capacity, less difference, the demand and capacity, as you see here, 1040 and 1030 are closed, right? uh, So we slightly increase the value of S prime and AS. The design will be adequate. You can increase. You can increase because if you are increasing the steel ratio, all right, the steel amount of steel, it will also increasing the capacity. But how much you have to increase? This is the question. Because if you are increasing in a large amount, so it will affect the value, the p value, the phi value. It will reducing the phi value from 0.90. Now the question is this, that how much we can increase and what amount of steel we have to increase, whether we have to increase the tension reinforcement, whether we have to make increase in tension, or whether we have to make increase in compression, right? We have to increase in compression or whether we have to increase the reinforcement in tension. This is the question. So as we already increased the amount of steel from 9.6 to 10.12, and here we are using the close value because the vertical S prime is 2 square inches and actual value is also 2 square inches. So that's why we will increase the S prime value, not disturbing the value of AS1, right? So the next question is there that how much we will increase the value of S prime, right? This is also important. So remember, you have to increase this by this amount, less than or equal to, not greater than, remember. Because if you are increasing this by certain amount, remember it will affect the value of P. This is very important point, right? So just increasing, just adding, increasing a little bit, increasing the S prime value. So we will check it how it works, right? So here you can see, note that the value of S prime is exactly the same as the theoretical value. S prime is theoretically same. The actual value of A is, however, is higher than the theoretical value by this amount. If a new bar selection for S prime is made, whereby the actual value of S prime exceeds the theoretical value by about this much, 0.52, the design will be adequate. Care must be taken not too much increase, then yielding criteria will be failed, and increase must be equal to or less than 0.52 inch. This is the point which I have already discussed with you people, right? Now, so let's say they just choose a bar, such a bar selection. They are increasing now, in the initial stage they are using two number 9 bars which give us exactly 2 square inches, but this time they are choosing 3 number 8 bar, right? 3 number 8 bar which give us a value of 2.36 inches. Now 2.36 inches means we are just increasing 0.36 square inches, which is less than 0.52, right, square inches. So let's see mm, whether it works or not. So once you increase the value, you have to again check the values of fc epsilon s prime, fs prime, epsilon t value, right? So assuming that fy equals to fs prime, right, we have to make this assumption, right, and calculate the value of c again by the same formula, s minus s prime. So s prime value is now changed. This is 2.36, right? So that's why we are recalculate the c value. And remember, here you need to calculate the a value first, and then we need to find out the value of c. Okay, so you can calculate the value of a, that is, as we are carry on in the initial state, that a value is as minus as prime divided by 0.85 fc prime, right, into b into fy, right? So this is a value, then you calculate the c value, which is a equals to beta 1, right? So here you see, but they just combine, they plug the value of a right here, and we got this final equation. So a is already known, is now this one, right? This one, because we changed the bar selection, right? And the b value is same, beta 1 is same, c value is now 10.74, fs prime value is recalculated, and here we are lucky that the yielding criteria still uh, exist or still prevail, right? While in that case, if you see here, fs prime is also here is 62 ksi, right, in that stage, and here it is 63.78, but here you can see here is 62.69. So still yielding criteria is fulfilled, and compression steel is yielding. This means compression steel is yielding. We need to find out the epsilon t value, and epsilon t value is 0.00482, which is, you can say, 48, very very close to 0.005. So p value, although 0 point, remember in calculating the epsilon t value you have to look to this digit as well. Okay, so this is 1 4 1 2 3 4, so you have to account for the fourth value as well. So this is less than that one, so that why this means p value is not equals to 0 0.9. So we have to find out the exact value from the same equation as we already used it. So now this is 0 0.88. Now this is important that at the first stage, in the first trial, the p value is 0 0.85. But here is 0 0.88, means the capacity is a little bit increased, right, by just 3%. Again, as the compression steel is yielding, this means fs prime equals to fy, right? And from this relationship, s prime equals to s2, I already discussed it. S prime equals to s2, this means 2.36. Remember, if this is not satisfied, then you have to recalculate your a is 2 from s prime fs prime divided by fy. Remember, if that condition is not satisfied, right? So, and s1 value will be s minus s2, this is 7.76 square inches, right? So again, checking the moment capacity, mn1 equals to s1 fy. Again, this is mn1, which is equals to 909.3 fit cap, and mn2, that is how much, 295. So just adding these two will give you the combined capacity, that is by mn1 plus mn2, multiplied this by the reduction factor, we got 1060 fit cap. Now this time is okay. Okay, so here we see that our ultimate movement capacity is now is how much, is the combination of mn1 plus mn2 multiplied by the reduction capacity, that is in this case is 0.88. We already calculated it, and at this time is capacity 1060, which is more than 1030, I think so. So here our design okay. So the design is okay now. Right here you see, this is the way, this is the calculation that you have to ensure your ductile capacity, ductile behavior, and you have to ensure the value of p. This is the complete procedure of designing a beam, right? Either it is a doubly reinforced beam, either it is a T beam, it is a slab. Okay, you have to check it, these things, if you want to a proper design. Although the question is finished right here, you can just simply says that this is very close to the required result, or so that why, or you can either uh, comment on this, that a little bit increase in the steel reinforcement like we did here, and that comment will also be worked, because in examination you have a time shortage, you can't do such lengthy calculation. So that why, to capture your time, you have to just write a comment that it can be increased by these kind of arrangements. Okay, this ends up this example. In next example, mm, in next example we will do some other example with the doubly reinforced beam, but I want to share this note. This note is very important, that 8 number 10 bar, 8 number 10 bar will not fit in a single layer in this beam. If they were placed in two layers, the centroid would have to be more than 3 inch from the bottom of the section. It would be necessary to check the arrangement. This is also important from your practical point of view. For your practical design, let me share this example with you people. I have designed this a single reinforced beam. You can see this is 20 inches. The effective depth is 17.5 inches. We placed 6 number 8 bars right here. So you see, when we calculate the spacing between these bars, so what we have, this is the 12 inches width, 6 8 by 8 are the total linear distance covered by these bars, minus 2 into 1 inch is the clear cover, minus 3 by 8 is the stirrup, right? So this gives us 3.25. So what will be the spacing between these bars? So the formula is this, that you just select this value and divide it by the spaces 1, 2, 3, 4, 5. We have 6 bars, then we have 5 spaces. If we have 10 bars, then we have 9 bars. So divided by 5, this is 0.65 inch center to center. So this is a small value. Remember, the spacing between these two bars should be how much? This is important. From ACI code, it is quite mentioned. If you go and search the ACI code criteria right here in this Nielsen book, right, mention here that the clear spacing of bars, okay, the clear spacing in bars, right, here, let me draw it, okay, this is, let's say, these two bars. So the clear spacing in this bar, and let's say here is the bar, this spacing, ACI code says that this spacing should be how much? It should be equals to the diameter of the bar, greater than the diameter of the bar, or it should be equal to it should be equal to 2 times of diameter of bar. Mean that we have two conditions, right? We have two conditions. One condition, that clear cover, this clear cover, this clear cover, it should be greater than the diameter of the bar, and this spacing and this spacing, it should be greater than diameter of bar. In next condition, it says that here you see, in second, clear spacing of the bars being developed are spliced greater than 2 dB, and clear cover should be greater than dB. Means in second condition that this spacing of the bars should be greater than 2 dB. So what is the effect? Effect is that if you are using the first condition, your development length will be this one. If you are not satisfying these criteria, you have to use this LD, or the development length criteria. What is development length? What does these equation means? I have already recorded 18 lectures over this available on my channel, right? So please go there and watch those lectures. These are the most important criterias, because if you're not satisfying these criteria, the ACI detailing criteria should not be fulfilled. And because you see here, you are 3 divided by 50, you can say you are increasing the development length, right? And here is the decreased value. So if your development length is increased, okay, like let's say your LD is 10 inches and your LD is 20 inches, so this is difficult to adjust in the beam section, while this is simple to adjust, okay. So that why basically we have to place the bars in such an arrangement that it will fulfill that is ACA criteria, the retaining criteria, right? But as here we are choosing 8 number 10 bars, so practically it is impossible to place such bars to satisfy these criteria that the spacing should be equals to diameter of bar. So what if you are placing the bars in two layers, it will further produce uh, another problem for you people, because as we are taking the effective depth from this layer, because we are assuming that we are placing the bars in one layer. Now if you are placing the bars in double layer, okay, so your D value will be decreased. If your D value is decreased from the previous one, so it will affect your moment capacity. It will affect the moment capacity. So let's say you detail this beam, the example which we do here, and find out the D value and then recalculate the moment capacity. So your moment capacity will again decreased. So this is again a problem for us. So to design a proper section, you have to maintain this check, as well as you have to adjust the p value. Then your design will be okay. Otherwise, your design will not fulfill the SA code criteria. Thank you for watching. See you in next lecture, which is in that lecture, this is 5.10.